All right, hello everyone and welcome to the lab. In this lab, I'm going to just go through the nuts and bolts of how to run the analyses that I described in the lecture on this birds and bats flight data. So the background to this data set is that scientists have recorded the energy usage of different species of birds and bats, and they want to know how mass affects those energy expenditures, but also whether energy expenditure differs among birds and different types of bats. So response variable is energy expenditure in watts, and then we have our predictor variables, which are mass in grams, and then type. And so this is the type of species that was being studied. And so it's a factor with 3 different levels. There's birds, echolocating bats, and non-echolocating bats. So we'll begin just by reading in the data. I better set my working directory. I'll read it in as flight. Let's just take a look at it. Looks like there's 20 rows and 1, 2, 3, 4 columns. I could use the dim command to double check that. And let's go ahead and I'm going to split my plotting window into 1 row and 2 columns. And then I'm just going to start by just taking a box plot and looking at how mass is affected or differs among the different types of species. Go ahead and look at that. Let me just make this a little bigger. And let's make a second box plot and look at how energy consumption differs among the different types of species we're looking at. And that did not work, and it's because I don't have my data set specified. Okay, so what I see immediately is pretty striking is that body mass is very different among these 3 different groups of species. So fruit-eating bats, non-echolocating bats, have the highest body mass on average. Echolocating bats tend to be very, very small, and birds are somewhere in the middle. They seem to have very different variances as well. And I can see a very similar pattern with energy expenditure. So it looks like the smallest groups of species have the lowest energy expenditures, and the largest species, fruit-eating bats, have the highest energy expenditures in watts. Now ultimately I want to investigate the effect of both mass and animal type on energy expenditure, and I'll do that using a multiple linear regression where I incorporate both of those predictor variables as potential predictors of energy consumption. But first what I want to do is make a scatter plot of how energy is affected by mass, and I'm actually going to color this scatter plot according to the type of species here. And that's where I specify this color is equal to type, which is a factor. And so what this is essentially doing is it's plotting this data in 3 dimensions. So I'll go ahead and run this. And why did that not work? Oh, you know what I'm going to do? I'm going to attach this flight data. And so again, this treats just each of my columns in my data set as independent variables outside of this data set, so I don't need to always use the $sign. Again, sometimes this is a good idea, sometimes it's a bad idea. Since we're only working with one data set in this case, this is probably okay to do. Let's attach that, and let's try running this again and see if it works. And it does. It lets me plot my legend correctly here. Let's just make this a little bit bigger. Sometimes you need to rerun this legend to make it work. Okay, so this is sort of a 3-dimensional plot because what I can see is that mass affects energy, but I can also see how animal type, whether it's an N-bat, E-bat, or bird, affects energy. And I can also look at the relationships between mass and energy for each of those types independently if I just ignore the colors of the other types. So I can see that black dots tend to fall along this positive line, red dots fall along what looks like a pretty similar positive line, and the blue dots, there might be a slightly different slope there for if I was to draw a line between them. But that's why we're going to use statistics to see if that slope really is different for this fruit-eating bats relative to birds and E-bats. A few other things that sort of pop out here. I see that a lot of my echolocating bats are located very low down here, okay, and I can see that the masses span 2 or 3 orders of magnitude. If I was doing this maybe for a publication, I might actually consider log transforming this mass, okay, putting this on a log scale, and sometimes that can actually linearize this data a little bit. Actually, let's just take a look at that just for fun, see what that looks like. And if you are really motivated, you might consider rerunning all the analyses I'm about to run, but with mass log transformed, and see if you arrive at any different conclusions here. So I'm just going to log mass there. Let's run it. That actually made it more curvilinear. So maybe that's not a great idea in this case. Okay, ignore what I just said. You probably don't want to go ahead and run all these analyses again because this data is highly nonlinear. Although I guess maybe one thing you could do is also log transform the energy values. Let's see what happens when we do that. And then if we look at the relationships between these now, okay, so now this is much more linearized. These orders of magnitude difference are sort of shrunk by putting both of these on the log scale. And we could still run all the same analyses treating log energy as our response and log mass as one of our predictors, and these would still be linear models. Our conclusions might change a little bit here. And doing this transformation might actually help with meeting some of the assumptions of linear regression. So maybe some of our assumptions won't be met eventually. So sometimes you can actually log transform your data or transform it in one of many ways to make sure that your data is linear, that the variance is constant, it looks like it's pretty constant here, and that your residuals are normally distributed. So I'm not going to do that in this lab, but if you want, go ahead and try running all the analyses with the energy log transformed and the mass log transformed, and maybe some of the assumptions will be more strongly met. Anyways, let's move on. So let's go ahead and fit some models to our data, and I'll just run this original figure first. Okay, so this is the data that we're trying to fit. And let's start by looking at an intercept-only model. Just change some of the margins here so that this white space up here kind of goes away and we're using the whole plotting window. So I fit my intercept-only model using this LM function, energy, tilde, and then 1. This tells me just the intercept. Let's take a look at the summary statistics for this. And as I described in detail in the lecture, so if you need to refresh on how to interpret some of these, because I'm going to go through this a little bit quickly to save time, this just tells me that the mean energy consumption across all my data points is 19.5, and it's significantly different from 0. So mean energy consumption of all my data is not equal to 0. That's not that surprising. And I could go ahead and just plot this, put a line here, a dashed line through that mean, and that sort of splits my data in half. Okay, now if I wanted to study the effect of mass on energy, so using a simple linear regression, instead of a 1 here for just the intercept, I'm going to put mass. Let's go ahead and run this, and let's also go ahead and plot it at the same time. Okay, so now it's fit a straight line through the data, a best fit line. So it crosses the y-intercept at 4.09. As we increase mass by 1 unit, energy consumption increases by 0.59, and this is highly statistically significant. So this model is telling me that mass has a significant positive effect on energy consumption. Larger animals use more energy. And we're explaining about 86% of the variation in energy consumption, and that's pretty good. Okay, now we might also want to test what is the effect of animal type on energy consumption, but not including that effect of mass. So in this case, what we're really doing with this model, energy as a function of type, is a one-way ANOVA. So maybe rather than representing this using a scatter plot, we want to represent it using a box plot. So that would look something like this. If I was to go box plot, energy as a function of type. Let's run that. Okay, and now what I'm testing with this model, energy as a function of type, is whether the means of these different groups differ from one another. And it looks very obvious that they do. So let's run this and just see. So I can see that the overall model is highly statistically significant. I see here that my reference group, which is birds, has a mean of 21.15. EBATs have a mean that is 18 units lower than birds, and that's statistically significant. So the difference between these two groups is statistically significant. And NBATs, non-echolocating bats, have a mean that is 9.8 units higher than birds, but it's not statistically significant. Now this ANOVA explains about 44% of the variation in data. So just these three different groups explain about 44% of the variation in energy consumption. That's not quite as high as mass, but again, this is statistically significant. And if I wanted to, I could just plot three different dashed lines here that are just fixed at the mean of those three different groups. Now next, let's look at an additive effect of mass and type. And so what this does again is it plots a best fit line for each of these different species, but the slope of those best fit lines is the same for all three species. It allows them to differ in terms of their intercept, so the lines can be higher or lower for each species, but their slope is going to be the same. So we'll run this, and I'm going to plot it at the same time. Let's just make my plot a little bigger again. Okay, and looking at my summary statistics here. So what this has done is it shows me that the relationship between energy consumption, mass and energy consumption has a slope of 0.057. So as you increase mass by 1 unit, energy consumption increases by 0.057, and that's highly statistically significant. Now for birds, the intercept of that relationship is at 6.02. The intercept for echolocating bats is 4.6 units lower than that of birds. And since the slope is the same, that means that for any particular mass, okay, whatever the energy consumption is for birds, the energy consumption for E-bats is going to be 4.6 units lower than that of birds. And for N-bats, it's 3.4 units lower than that of birds. So N-bats are in the middle here. Now these differences are not statistically significant. So in reality, this model is sort of telling me that there's really just one slope and one intercept that describes all three species at the same time. So I'm not really getting that much extra by including animal type in addition to mass. I can also sort of get at that by looking at this R squared. It's 0.879. And my R squared, again, the proportion of variation in energy that's explained by my predictors, was 0.86 when I only included mass and I didn't include type. So I've really only increased by about 2% by including this extra variable animal type. Okay, the overall p-value for the model is still highly statistically significant, but a bunch of the effects in this model are not. So finally, let's look at an interactive effect between mass and type. So does the slope differ for each of these different species? So maybe some of them have a different relationship between mass and energy than others. So we'll run this and plot these effects. And so we can see here that the slope for N-bats looks like it's a little shallower than that of birds or E-bats. They have different intercepts as well. If I look at the summary statistics for this final model, I can see that the effect of mass is highly statistically significant, but none of the other effects are. So the differences in the intercepts and these interactive effects of mass and bat type or animal type are not statistically significant. I'm now explaining about 90% of the variation in energy consumption, so even higher than any of the other models, but not that much higher, and my p-value overall is statistically significant. Now, as we talked about in the lecture, the question then is which model should I use to draw conclusions from? So I explain more variation than any other model when I include all of these effects, but a bunch of them are not statistically significant. And we saw from the individual models, LM2, that included the effect of type, this model was statistically significant, but LM1 was also highly statistically significant. And these other models, LM3 and LM4, were statistically significant as well. So what I want to do is choose a model that fits the data adequately, but doesn't use too many parameters. Okay, so we haven't overfit the data. So it's balancing goodness of fit with model simplicity or parsimony. So if you need to, you want to install this package BBMLE. I'm going to load it. And then I'm going to run this AIC table. I include all my models in there. And then I also want it to print the weights, the base, so this is the likelihood, and the log likelihood. So let's go ahead and run this. Gives me an output, looks something like this. And the model at the top is the one with the lowest AIC value. Okay, so its delta AIC is always going to be 0, and then we compare all the other models to the top one. So LM1 here is my best model. The next best model is 3.6 AIC units higher, and that's a fairly significant amount. And if I look at these weights, I didn't talk about this in the lecture, but these weights tell me the proportion of evidence. These weights give me some indication of the proportion of evidence that's encapsulated by this model. So this model has 84% of the weight. Okay, my next best model, LM3, only has 14% of the model weights, and the rest of them almost have 1 or less than 1. So clearly my top model, LM1, is performing much, much better, almost 7 times better than my next best model. It has clearly the lowest AIC, uses only 3 parameters here. And so in this case, I'm going to settle on interpreting the results from LM1. And again, just to refresh, LM1 was my model that only includes an effect of mass, and it doesn't include these extra effects of animal type in addition to mass. So essentially, we can say something about energy consumption if we just know about the animal's mass. We don't even need to know much about whether it's a bird, an echolocating bat, or a non-echolocating bat. Okay, because mass tends to scale with energy in the same way for all 3 different species. Now finally, let's just take a look at some diagnostic plots and check our assumptions based on this top model. So let me just actually draw the figure for this top model one more time, just so we have this fresh in our mind. Okay, and I'm going to load a few libraries that I need here. So this car library, GVLMA, and this mass library. And we'll start just by assessing outliers here. So it does look like there might be some outliers up here. So I'm going to split the plotting window in 2. Let's take a look at the QQ plot for the studentized residuals. And what I would like to see, let's do this one more time, from this QQ plot is that the observations tend to fall along this 1-to-1 line. I can see there actually are some significant departures up here. And I do want to see that these points are within these sort of confidence intervals. And some of these points are sort of approaching the outside of these confidence intervals, so that's maybe not good, but there's only 1 or 2 of them that are out there. So I might have some departures from normality and some outliers here that I might be a little bit concerned about. And maybe then I would want to consider log transforming my y and my x values like I did in the beginning of the lab. Maybe that would deal with some of these issues. Here in these leverage plots, again, I want to see that these points tend to be clustered around this red 1-to-1 line, and that they tend to have the same variance as you move along. I can see that there does appear to be a little bit of a change in variance here as you move from left to right, but they do tend to be generally clustered along that line, so that's pretty good. Okay, there aren't any major outliers. I could use that outlier test as well to check on this. We did that last week. Now, assessing the normality of my residuals. So I'm going to use this student residual command to calculate the studentized residuals of my top model. And then what I'm going to do is plot a histogram of those residuals and then overlay that with a perfect normal distribution to just sort of take a look at how well they compare to a normal. So let's go ahead and do that. And what I see is that they look somewhat normal here, but I do see that there appears to be a big long tail out on this end of my actual residuals, okay, that are represented by these boxes, this histogram. And it looks like my data is sort of truncated on this side, so a really perfect normal distribution would continue way out here, okay, it would be perfectly symmetrical. So my actual data doesn't necessarily look perfectly symmetrical here. So maybe there is a little bit of departure from normality in my residuals. Let's just do a Shapiro test to confirm that. And I see that my p-value is extremely low. So that again suggests that my residuals are probably not normally distributed in this. So I've sort of violated that assumption of normality. Now finally, let's evaluate this homoscedasticity assumption. So I sort of did that above with my leverage plot. But I can use this NCV test command to formally test for this non-constant error variance. And when I do that, I arrive at this p-value of 0.06, so that's approaching statistical significance, but maybe isn't quite there yet. So maybe I can actually be somewhat confident that my error terms are actually constant as I move from left to right. I could visualize this again just by plotting the studentized residuals against the fitted values. And what I should hope to see is that I move from left to right, they stay somewhat within the same bounds. It looks like actually it's getting a little wonky out here. That makes me a little bit suspicious that maybe this NCV test isn't telling me quite what I want. Maybe that's why it's approaching statistical significance with this 0.06, because we're starting to get crazy variance out here on the right. And in this case, if I plot the residuals versus the x values, I'll get essentially the exact same thing, just rescaled. Okay, so my homoscedasticity assumption is maybe met here, maybe not. It's a little hard to tell. Again, I might want to consider transforming my data. And finally, let's just do a global test of the model assumptions using this gvlma command. I like to use this one because it gives me a nice summary of a few different tests all at the same time. So let's go ahead and run this. And wow, and I see that a bunch of the assumptions are not met. So my global statistics are not met. I haven't talked about the skewness, kurtosis, and link function yet, and we're actually not going to focus on that too much. Okay, but I see that there's something weird going on here. Don't like to see that. And it is telling me that this heteroscedasticity assumption is okay. So actually, my variance isn't increasing significantly as I move from left to right here. Okay, so I have violated some of the assumptions of linear regression, and it's sort of, this is where the art of statistics sort of comes in. So you might decide that your assumptions have been so wildly violated that you need to rescale your data in some way or analyze it in a different way. We're not going to get too much into that here, okay, other than just to be aware that you need to pay attention to these assumptions. Now we could go through several lectures on assessing these assumptions of linear regression and how to deal with cases when they become violated, and oftentimes they will be, and how to decide when they're so wildly violated that you do need to switch to a new type of analysis. We don't really have time for that in this course, but what I will suggest is if you do want to read more about this, there are a couple resources you can check out. So there are two books written by John Fox that you can check out. One is Applied Regression Analysis and Generalized Linear Models. Okay, a great resource on just how regression works and how these more complicated linear models can be fit. And there's also a book on this companion book to linear regression that you can check out that deals with some of these assumptions. But now we're in 2016. You can also Google all of these topics and get really detailed results, detailed explanations of what you need to do. So definitely don't underestimate what you can find on Google, and I really recommend that you spend some time checking that out on the internet if you feel a little uncomfortable or fuzzy on some of these topics. Okay, well that wraps up the lab this week, so good luck everyone in the assignment. Use the discussion boards as much as you need to, and I will see you next week.